Hi everyone! Welcome to part 1 of chapter 17. Today we are going to start our chapter on aqueous ionic equilibrium. This chapter is going to look at reactions that are done in water and form an equilibrium. The first of these types of reactions that we're going to look at is buffers. Buffers are going to be made up of weak acids and their conjugate bases, or weak bases and their conjugate acids. And buffer solutions are really great because they can kind of mitigate changes in pH so that the pH will stay the same even if you add a little bit of acid or add a little bit of base. A really good example of a buffer that you'd be familiar with is your blood. Your blood works to keep your body at approximately the same pH all the time. So that's what we're going to cover today. Okay, so buffer solutions. Buffer solutions are solutions that resist a change in pH when you add either a base, right? So that would be hydroxide, or protons, which would be, hydrogen from an acid. And the buffer resists the changes in pH by neutralizing the added acid or the base. And so like I was saying earlier, a buffer solution contains either a weak acid and its salt, which means the conjugate base, or a weak base and its salt, which means the conjugate acid. Okay, and so they're always going to have these acid-base pairs. Like I was saying, your blood is a buffer. It's a mixture of carbonic acid and bicarbonate, and it works to keep your body at approximately the same pH all the time. So the way that we would make a buffer is we would put in a weak acid and the conjugate base. It has to have both of those things in order to be considered a buffer. So like in our example here, we have acetic acid and sodium acetate. And when sodium acetate, right, when you put that in water, it's going to break into sodium and acetate. So acetate is our conjugate base of our weak acid, right? They differ only in that proton, only in that H+. So this would be an appropriate buffer solution. And this is going to be an acidic buffer because we're starting with the acid and its conjugate base. You can also make basic buffers, which we're going to talk about a little later. So here's some examples of some acid-salt buffering pairs. Okay, the salt will always contain the anion of that weak acid. Okay, so like, for example, this first one, we have hydrofluoric acid. If we take off that hydrogen, then we would get, F-, we'd get fluoride. And in order to, have it as a salt, right, we can't just have these fluoride ions, we will need to either add on a sodium or a potassium. And the reason that we add one of those is that they are both soluble in water, so that we know that our salt is going to be soluble. And sodium and potassium are the cations of a weak base, the cations of a strong base. And since we know that they are cations of a strong base, that means they don't have any acidic or basic properties. So both of these will cause a neutral pH. So they're not going to affect our buffer at all. So our buffer then will only depend on our weak acid and our conjugate base. So again, all of these salts, right, we're just going to kind of take off the sodium or take off the potassium to see what that, conjugate base would be. But again, all of these are going to differ, just be from one will have a hydrogen and one will have that cation of a strong base. So this is how they work. So if we have an acidic buffer, we're always going to have our weak acid and we're going to dissolve it in water, but we will also have some conjugate base there. And the way that that's going to work, right, we're going to end up with some, hydronium ions floating around. So buffers work by applying Le Chatelier's principle to a weak acid equilibrium. Okay, again, they're going to have a bunch of these weak acid molecules and a bunch of the conjugate base molecules. And so if we happen to add some base, the base would react with the weak acid and it would form conjugate base. But we already had a bunch of conjugate base in there, so it's not going to change the pH that much because our ratio of this weak acid to conjugate base isn't going to change a whole bunch as long as we don't add very large amounts of this strong base. Another way to think of it, if you want to, is you can think of the hydroxide combining with the hydronium up here, which would cause us to decrease our hydronium ion concentration and shift to the right to make more of our conjugate base. Okay, to make more of our hydronium, which increases our concentration of our conjugate base. But again, we're just kind of shifting the position of the equilibrium. right? We haven't, we haven't overwhelmed our buffer. We haven't added a ton of our strong base. We're just kind of shifting the amounts of our weak acid and our conjugate base. So if a strong base is added, like we were just talking about, it's going to be neutralized by the weak acid that's in the buffer. So if we have acetic acid and we add some sodium hydroxide, then they will react, they will produce water and some sodium acetate. So again, we're still going to have, we're going to have weak acid and conjugate base, which means we'll have a buffer. So as long as we are only adding a very small amount of sodium hydroxide, we're still going to have both of these two things in solution, so our pH is not going to change all that much. So here's kind of a picture image, a diagram, if you will, to see how the buffers work. So if we're going to add some hydroxide, that will react with our weak acid, and when it does that, it's going to produce some conjugate base. And so now we are going to have more conjugate base than we started with, but we still have weak acid and conjugate base in solution, so our pH is not going to change all that much because we still have acid and base. So it can't be all that acidic, it can't be all that basic because we have both. So if we were to add an acid, right, we just talked about adding a base, but let's say instead that we added an acid. Okay, well our acid is going to react with the base that's in our buffer. Okay, so we have our weak acid and our conjugate base, so if we add some H plus or H3O plus, then that will react with our acid and shift the equilibrium the other way. Okay, so our acid combines with our conjugate base to produce more of the weak acid. But again, as long as we are not adding very much of our acid, then we're only going to shift the equilibrium slightly. Our relative amounts of these don't change a whole bunch, which means that our pH will stay approximately the same. So here's an example. If we have some strong acid, right, some hydrochloric acid, and we add it to the sodium acetate in our buffer. Okay, so our hydrogen is going to combine with our acetate, and it's going to make acetic acid and sodium chloride, which doesn't have any acidic or basic properties. So again, though, we're still going to end up with weak base and conjugate acid, and as long as we keep this amount of acid that we added, the strong acid that we added, fairly small, then our pH change is not going to be very large. So here we go, another diagram. So this time instead, we're going to add acid. So our acid will react with our weak base. It's going to produce some more weak acid, and that's going to increase our concentration of weak acid. But again, we're still going to have weak acid and conjugate base, so our pH is not going to change all that much. So here you go, all together. If we have equal concentrations of weak acid and weak base, that would be a good buffer. Okay, that's we're going to talk about this, more toward the end of this lecture, but ideally to have a really good buffer with really good buffering capacity, you're going to want to have approximately equal amounts of your weak acid and your conjugate base. So whether you add either acid or base, right, it can mitigate those changes. So if we add acid, it's going to react with our conjugate base. And when it reacts with our conjugate base, it produces more weak acid. So we're shifting our equilibrium toward the weak acid. So our pH will become slightly more acidic. Not a lot more acidic, but slightly more acidic. If we add hydroxide, then that is going to react with our weak acid, and it's going to produce more conjugate base. And so we're going to shift our reaction toward being a little more basic. But again, we're not shifting it all that much. It's not like we just added some acid, if we added some strong acid to water, that would make it super acidic. Or if we added some strong base to water, that would make it super basic. But since we have this buffer that can, react with, the added strong base or the added strong acid, it's neutralizing that and producing a weak acid or a weak base. And we have the conjugate that's also in solution, which means our pH is not going to change that much. So to sum it all up, if you add hydroxide to a buffer, then it will react with a weak acid to produce some conjugate base and water, of course. But our ratio is not going to change very much. That's the key. So since our ratio of weak acid to conjugate base remains essentially kind of constant, our pH isn't going to change all that much. Same thing if you add an acid. If you add an acid, it's going to react with the weak base to produce more weak acid. But again, the ratio is not going to change very much, so our pH doesn't change. So all of this is because of this common ion effect. Okay, so if we look at our weak acid and our conjugate base, they have this, ion, this A- in common. Okay, so rather than if we just had a weak acid and say we added some strong acid, that would overwhelm our weak acid and make it really acidic. But if we have our salt in there, we add our salt that has this conjugate base with this common ion, it will, then we can, mitigate these changes in pH because we can have added acid react with our base or added base react with our acid. Okay, so if we add a little bit of our salt, so say we have a buffer that looks like this, and we add a little bit of our salt, NaA, right? And in water, that's going to dissociate into Na plus and A minus. Okay, so if we add some salt to this existing buffer, that is going to increase our concentration of this A minus, and it's going to shift our equilibrium to the left. Okay, when we do that, it's going to decrease the concentration of our hydronium ion because, right, it's on the side that we are using up. We're going to use up all of the stuff on the right because we're shifting to the left. So by adding this, this salt, we are decreasing the pH because we have shifted our equilibrium to the left. Okay. Another way to think about it, this would be how I would want you to think about it and talk about it, but another way to think about it is, okay, if I put this salt in here, I know that sodium doesn't have any acidic or basic properties, but I know that this A minus, right, it's negatively charged, an anion, therefore it is going to act like a weak base in solution as long as it's, not like chlorine or nitrate or something like that we've talked about previously that doesn't have acidic or basic properties. But if it's the conjugate base of a weak acid, then it's going to act as a weak base in solution. And therefore, if you're adding a bunch of weak base, it would make sense that your pH is going to go up, right? It's going to become more basic. And the way that it does that is because this weak base is reacting with the hydronium ion, and it's going to make more weak acid. Okay? All right, so if we just had our weak acid by itself, you can see that it has an acidic pH. It doesn't have a really acidic pH. Like a strong acid would have a pH of 1 or, even lower. Sometimes it can be negative. It's so, it's so concentrated. But this pH around, 2 or 3, sometimes even like 3.5, that's really characteristic of a weak acid. And then here we have our weak base, right? We have a conjugate base of a weak acid. And so as you can see, it has a basic pH, right? It's not really basic because it's a weak base, but it is above 7, therefore it's basic. When we have both of them in solution, though, our pH falls somewhere between there, right? And because now we have weak acid and conjugate base. As you can see, the pH is not at 7. And this is because this pH that we see with this mixture, this is going to be based on the Ka of the acid. Okay, you can think about this as our acid is a stronger acid, right? Even though it's a weak acid, it's a better acid than it is a base, so it's going to have a lower pH than 7. But we're going to base this all on calculations, so you'll get the Ka and then you'll look at the pKa to figure out what this pH is. So we can calculate the pH after, calculate the pH of our buffer after we add an acid or a base by breaking our problem down into 2 different parts. The first one, we are going to do a stoichiometry calculation to figure out this reaction of whatever we've added. So if we've added acid or we've added base, we're going to use that to react with one of the ingredients of our buffer and figure out what's left after the reaction. When you do this reaction, make sure that this is always done in moles, okay? This is a stoichiometry calculation. Make sure you're not in molarity. You have to be in moles. And typically, we are going to make these one-way arrows because we're going to react this with a strong acid or a strong base, and so those will both react completely. So we'll use these as single-headed arrows. After we do this reaction and we figure out what's left in solution, then we can do an equilibrium calculation to figure out our concentration of the hydronium ion and our pH and anything else that we need to figure out after that. All right, so when we add a strong acid or a strong base to our buffer, again, this is going to be a neutralization reaction. So we're going to use these single-headed arrows for this. So if we add, if we are adding acid, then we'll write it this way. If we are adding base, then we will write it this way. But by knowing how much acid or base that we add, we can figure out how much of our weak acid or our conjugate base is formed, and we can figure out our buffer. So after we figure out the new concentrations of the weak acid and the conjugate base, then we can figure out the pH using this Henderson-Hasselbach equation. And I want to note before we go forward, once we have added this strong acid or this strong base and we do the neutralization reaction, the concentrations of our weak acid and our conjugate base will be different, aside from the reaction, but they will be different than they were before because we will typically have a change in volume from this strong acid and this strong base. So remember this calculation that we were doing before, that has to be in moles. And then after we get the moles of the weak acid and the conjugate base that are left over from the neutralization reaction, then we can use the total volume of the solution to calculate the new concentrations of these two species. So make sure you take that into account. Then we can calculate the pH using this Henderson-Hasselbach equation. And I want to be very, very clear, this can only be used for buffers. It's essentially kind of a shortcut. Instead of using this equilibrium ice table and going through the whole Ka process and finding the pH from that, this is kind of a shortened procedure for this whole thing. So this Henderson-Hasselbach, really, really cool, only for buffers. So be very, very careful. You must make sure to have a weak acid and the conjugate base or a weak base and the conjugate acid. If you start trying to use it with strong acids or strong bases and things like that, it will not work. So be very careful. I've said it a bunch of times because I see people do it all the time. Anyways, the Henderson-Hasselbach equation is that the pH is equal to the pKa of the acid plus the log of the base over the acid. And I've written it this way. This is how I like to remember it, base over acid, because sometimes we will use this for a weak acid buffer, and sometimes we'll use it for a weak base buffer, but you can use it for both. It's always going to be pH, it's always going to be pKa, even for a base, so be careful, you'll have to calculate the pKa, and then log base over acid. Okay. In this case, since we have an acid buffer, we're going to put HA on the bottom, which is our weak acid, and our conjugate base on the top. So it's derived from the Ka expression, like I said. If you go through the equilibrium ice table and you have the buffer and you went through and to calculate all of that, the pH from that, the hydronium ion concentration, you would come out with the pH is equal to the pKa plus log base over acid once you finish all of the calculations. So you would go through all of this to get the pH. So if you're really interested, the derivation is in your textbook, pages 784 to 785. I'll let you look through it. Otherwise, you can trust me that this is how it does work out. But the equation will calculate the pH of a buffer, like I said, pKa, and the concentrations of our acid and our base after the neutralization reaction, as long as we can use this X is small approximation. And, when we can use that X is small, that's when we're looking for, very, very small values of K. We're never going to use it for very large values of K because that would signify that we have a strong acid or a strong base. And I just told you this can only be used for buffers. So this will be when, our K value is very, very small. We're looking for, times 10 to the minus 3 or smaller. Okay, so like I was saying before, the Henderson-Hasselbach equation will work really well when we have that X is small approximation that we can use. If we can't use that approximation, you'll have to go through the ICE table like we normally do with the Ka expression and solve for the hydronium ion concentration and then plug that in for pH and all of that. But the X's small approximation will work when both of the following are true, okay? So the Ka is very small, it's what we were just talking about, and we need the initial concentrations of the acid and the salt to not be super dilute. If they were really, really dilute, then those concentrations would be very small, and that X could be actually playing a factor into our concentrations. For most problems, though, like I said, this will be totally fine because we can't use it for our strong acids and our strong bases anyway. All right, we're going to start working through some practice problems. In this chapter, I'm going to include a lot of practice problems because it's a very math-heavy chapter and you need to see a lot of examples. If at any point you feel confident enough to work through the problem on your own, pause it before you get to the answer. I'll always have the problem like this and then the answer on the next slide. So if you want to, you can always pause and try and work through it yourself before coming back and seeing how to do it. All right, so for this first one, we are going to get some practice using the Henderson-Hasselbach equation. So this says, calculate the pH of a buffer solution made from a 0.2 molar acetic acid and 0.5 molar acetate solution. So we have our Ka there, which we'll need in order to calculate the pKa. So here we go. Since we have a weak acid and its conjugate base, that means that this is a buffer. Remember, you're always looking for those two things in order to have a buffer. Since we have a buffer, we can use the Henderson-Hasselbach equation, which is awesome. It's a shortcut. So we have pH equals pKa plus log base over acid. So we have our concentration of our base, right? That's our conjugate base. We have our concentration of our acid, but we don't have the pKa. We have the Ka. So the way that we calculate the pKa is we take our negative log of our Ka. So I have that there. That gets us 4.74. Remember, I'm never going to ask you to memorize any Kas. Those will always be given to you. So now that we have the pKa, we can go ahead and plug this in. So we have pH is equal to pKa plus log of our base, which is our acetate, over our acid, which is acetic acid. Once you calculate that, 5.14. And that makes sense because if we look at our relative concentrations of our weak acid and our conjugate base, we have more base than we have acid. If they were equal, then our two values in this logarithm, like this, our base and our acid, those would be equal. And if they are equal, then we are taking the log of 1, and we take the log of 1, that's 0. So this whole thing would go to 0 if that was equal, and then pH would be equal to the pKa. However, in this buffer, they're not equal, and we have more of our base than we have of our acid. And since we have more base, our pH is coming out more basic than our pKa. So that makes sense. That's always a really good check to make sure that you've done everything correctly and, put things into your equation in the right order. All right, let's try another one. So this is a solution was prepared by dissolving 0.2 moles of acetic acid in water to give 1 liter of solution. And I want to know what's the pH. Okay, so looking at this, we do not have a buffer. All we have is acetic acid in water. We've seen that problem before. That is a weak acid equilibrium. Okay, and you might be thinking, well, okay, that's weird. What's it doing in this chapter? I promise we're going to use it in the next practice problem, but I want to review how we would solve this weak acid problem because we're going to use it later in this chapter. So we have a weak acid equilibrium problem. So instead of doing an ice table in moles, right, we're going to do this in molarity. Remember, we are always going to do stoichiometry, right? Reaction ice tables, those are going to be in moles. But whenever we're going to do an equilibrium ice tables, those will always be in molarity. So here's our equilibrium. We have our acid reacting with our water to produce our conjugate base and the hydronium ion. So here's our ice table. We have our initial concentration of our acid. We don't have any of our acetate or hydronium. And then we do our minus x's, plus x, and then we add those down. And then we can put that into our Ka expression. We know that since our times 10 to the minus 5, this Ka value is very, very small. So that means our change in our initial concentration is negligible. So we can get rid of that minus x and it just becomes x squared over 0.020. And we can go through and solve for x. Okay, we'll multiply both sides, take the square root, And then that will give us our hydronium ion concentration, which we can then plug in to our pH equation and calculate the pH. So I'm zooming through this because I assume that we all know how to do this because we have already covered this chapter. All right, but in the next problem, we're going to take that solution from our last problem, right, that weak acid, and we are going to add some concentrated sodium hydroxide. Okay, so we're going to say that there's no change in the volume. We're just going to add some moles of sodium hydroxide. Maybe it's, you know, little pellets. And I want to know, what is the new pH? Okay, so we have acetic acid, and now we are adding sodium hydroxide. So we have a weak acid, and we are adding a strong base. When that happens, we are having an acid-base reaction. Okay, so since we are having a reaction, right, we have a weak acid and a strong base. This is a reaction. That means we need to do an ice table in moles because we have a reaction. And then we'll figure out what is left in solution after the reaction. In this chapter, this is usually how your problems will go. You're going to have an acid and a base. They're going to react, and you're going to do a reaction ice table and figure out what's left over. Okay, that's really, really important because the stuff that's left over, that is what is going to determine our pH. So our first thing we need to do, we need to write an equation, right? So we have our weak acid and our strong base, right? Because sodium hydroxide in water, sodium hydroxide will give us sodium and hydroxide. So we have our weak acid reacting with our strong base to give our conjugate base and water. So we'll go ahead, we'll make our ice table, and we need our moles. So we have our moles from our last problem. We have 0.020 moles of acetic acid, and we have 0.008 moles of sodium hydroxide. We don't have any moles of our acetate because we didn't put any in there, and we're not going to worry about water because it's in water anyways. We have lots of water. So when we are doing these reactions, we are always going to subtract the smaller value. Typically, and I would say like 95% of the time, I'm always going to give you, well, not always, but I will mostly give you acids and bases that react in a 1-to-1 ratio. And as you can see here, we have one acidic hydrogen and we have one hydroxide. So they're going to react in a 1-to-1 ratio. So we don't need to go through and figure out which one is going to be limiting. You can actually just find the one that's smaller. So if we look, 0.020 versus 0.008, 0.008 is smaller, so we're going to use that as our change value. Remember that this is going to react completely, so we're going to subtract all of that. So we're going to go minus 0.008, and then we're going to add it to the other side. And when we do that, we can add it straight down. We'll have leftover weak acid. We'll have no more strong base, but we now have conjugate base. So look, we have weak acid, we have conjugate base. That means we have a buffer. So by adding strong base to our weak acid, we converted some of the weak acid into conjugate base, and now we made a buffer. Okay, so now the way that we can calculate the pH is we can use the Henderson-Hasselbach equation. So we have pH is equal to pKa plus log base over acid. So remember, we did this table in moles, but our Henderson-Hasselbach, see these brackets? We need those to be in concentration. So we should have to go through and calculate the concentration from these moles, right? We have moles, we have 0.008, but we don't have any volumes up there, right? So ignore the changes in volume, but we have 1 liter of solution here, so we divide those both by 1. So when we divide those both by 1, we would get the same value, right? Our moles and our molarity, it's going to be the same. So in this case, it doesn't matter that we're not going to go through and calculate molarity. I am going to tell you a shortcut here. The way that this works out, when we put, say that we had, we put 0.008 over 1, and then we had 0.012 over 1, right? Those are both, the ones are our liters and the others are our moles. Do you see that they would cancel out, the numbers on the bottom? They're going to be the same. They're always going to be the same because it's in the same total volume. So that will cancel, and we could have just put moles in the first place. So a lot of times after this step where we do stoichiometry, you're going to see me omit these volumes here and actually use moles in the Henderson-Hasselbach because it won't change the value. Okay, but I want you to be very, very careful. You can only do this if the volume is the same for your moles of base and your moles of acid. If there's at any point that they are going to be different, then you would need to go through and calculate those concentrations before putting them in this equation. Okay, back to this. So our pH is equal to our pKa plus log base over acid. So we can calculate the pKa again. I did it on the previous slide, but we can do it here. And so we've got our pKa. And then we can plug it in to our Henderson-Hasselbach. This is our conjugate base, so that will go on top. That will be the weak acid, so that one goes on the bottom. And then we have 4.56. So in looking at this, that makes sense. In this case, we have more of our weak acid than we have of our conjugate base. So our pH is lower than our pKa in this problem because it is slightly more acidic, right? We have more acid. So, like we've been talking about, buffers resist changes in pH when acid or base is added to them, but their pH does change a little bit. That's what I've been talking about or trying to point out. When we get to the end of our problem, if we had equal amounts of our buffer, the pH would be equal to our pKa. But if we have slightly more acid, then it will be slightly lower than our pKa, and if we have slightly more conjugate base, then it would be slightly higher than our pKa. So it does change, right? Remember, they were always going to do two parts to these buffer problems. The first part is going to be that stoichiometry ice table, and then the second part will always be that Henderson-Hasselbach equation. That Henderson-Hasselbach equation, we can only use that if we still have a buffer. Sometimes you will add too much acid, right? Too much strong acid or too much strong base, and it will overwhelm your buffer. If you add more moles of your strong acid than you have of your conjugate base, or more moles of your strong base than you have of your weak acid, then those will overpower your buffer. They will take over. You won't have a buffer anymore. Okay, so always just be careful. Don't just throw things into a Henderson-Hasselbach because you thought it might be a buffer. Always double check. So let's try this. So what is the pH of a buffer that has 0.140 moles of hydrofluoric acid and 0.071 moles of potassium fluoride in 1 liter of solution when 0.020 moles of hydrochloric acid is added? So in this problem, we have a buffer, right? We have a weak acid and a conjugate base because in water, Kf will give us K plus and F minus. Okay, so we have a weak acid and a conjugate base, but now we are going to go add hydrochloric acid to our buffer. And so we need to figure out, okay, after that happens, do we still have a buffer? And regardless, what's the pH after the reaction happens? So we are going to add in the hydrochloric acid. Hydrochloric acid is going to react with our weak base. Right? So this, again, is going to be an acid-base reaction. So we need to do a reaction ice table, again, in moles to determine what's left in solution after the reaction. So I've written it this way with the conjugate base on the left because that's the part that's going to be doing the reacting. You totally could have written it the other way and that would have been fine. Just make sure you're always paying attention to where your initial values are going. So we have an ice table. So we have our fluoride, and we have our, this hydronium ion, this is going to be our acid, so this is our HCl. Remember that when we put HCl in water, it breaks into H plus and Cl minus, and that H plus will bond onto a water molecule, giving us H3O plus. So we have our fluoride and our strong acid and our hydrofluoric acid. So again, remember, this reaction will go to completion because it's a strong acid reacting with our weak base. Okay, so we can think of that as being a single-headed arrow to the right. So we look at just which one of these is smaller. So our 0.020 is smaller, so we're going to subtract that, and we'll add it to the other side because when that strong acid reacts with our conjugate base, it's producing more weak acid. Okay, then we can go ahead and we can add them down, and we can see what's left afterwards. And so now we have conjugate base, weak acid, so we have a buffer. Okay, Now that we have a buffer, we can go ahead and plug it into our Henderson-Hasselbach equation. pH equals pKa plus log base over acid. So we were given our pKa, which is great, and then we can just plug in our concentrations, right? Again, since we have our values and it's 1 liter of solution, these end up being our molarities, even though they were moles in this ice table. So we can plug those in. Our weak base will go on the top, and our weak acid will go on the bottom, and we can plug it in. If you look, we have more of our weak acid than we do of our conjugate base. Therefore, our pH is coming out more acidic than our pKa. So like before I was telling you, we can make our buffers out of weak acids, but we can also make basic buffers. And the reason that we might make a basic buffer over an acidic buffer depends on the pH of the reaction that we're doing. Maybe we need a solution in which we need a basic pH in order for our reaction to go. Well, maybe we would make a basic buffer to help that out. Okay, we don't always want it to be acidic, but you would do it the exact same way. You would have now a weak base and its conjugate acid. Okay, but again, you have to have both of those pieces in order to have a buffer. So here are some examples of our weak bases and our salts that can go, that can be our weak acids. So something like ammonium chloride, remember, would break into NH4 plus and Cl minus in solution. We want to have an anion of a strong acid, so like this came from hydrochloric acid, this came from nitric acid, right? Because neither one of these two ions has any acidic or basic properties. So they are going to be pH neutral, and we can just look at our buffer with our weak base and conjugate acid. So the Henderson-Hasselbach equation also works for basic buffers. There's actually another form of the Henderson-Hasselbach equation that you can use, and it solves for pOH and it uses pKb and all of that good stuff. But I think that that's just one more thing to remember, and the Henderson-Hasselbach equation that we were just talking about works just as well for basic buffers, and I'm going to show you how. Typically, though, the way it was written, the way that we have been using it, is for a weak acid reactant and the conjugate base as the product. But if we have a basic buffer, then our weak base is the reactant and the conjugate acid is a product. So it's essentially backwards, right? So our base is over here and our acid is over here instead of vice versa. But to apply this Henderson-Hasselbach equation, we can just look at it as being backwards, okay? So it's the exact same thing, right? So now we have an acid on this side and a base on this side, okay? All we've done is taken our base and looked at it, taken our conjugate acid of our weak base and thought about it as an acid in water, producing our base and hydronium. So if this is confusing, don't worry too much about this. The long story short is that this doesn't affect the concentrations at all. It just affects the way we are looking at the reaction, and we can still use the equation just the same way. Our pH is going to equal our pKa plus log of our base over our acid, okay? Nothing is changing. We're still using pH equals pKa plus log base over acid. The only thing that's going to be a little bit of a pain is to figure out the pKa, because normally you'll be given Kb, and from that you can find Ka, and then you can find pKa. So it's just one more step, but now we have a Henderson-Hasselbach equation that we can use always rather than just for acids and having to remember another one for bases. pKa and pKb are related, just like we have a relationship between Ka and Kb. Like we know Ka times Kb will give us Kw, which is 1.0 times 10 to the minus 14. So if we take the negative log of all of this, right? We take the negative log of our Ka times Kb, we take the negative log of our Kw, and we take the negative log of 1.0 times 10 to the minus 14, which gives us 14.00. We can go through and we can actually derive the relationship between pKa and pKb. So the way that this works, right, the way that this log works, when you have things inside the parentheses that are being multiplied together, you can add together their logs. So we've separated it back out by putting plus the two logarithms is equal to 14. And we've just kind of dropped this Kw because nobody really cares anymore. If we take the negative log of the Ka, that gives us pKa, and we take the negative log of Kb, that gives us pKb. So pKa plus pKb equals 14. So if you have the pKa, you can really easily find the pKb because you'll just subtract it from 14. Similar to like pH and pOH, same relationships work for pKa and pKb. All right, let's try another practice problem. What is the pH of a buffer that is 0.50 molar ammonia with a pKb of 4.75 and 0.20 molar ammonium chloride? Okay, so we have a weak base and its conjugate acid, so this is a buffer. Okay, but this is a basic buffer, so I'm going to show you how the Henderson-Hasselbach works just the same with this basic buffer as it did with our acidic buffer. All right, so here we go. We have a weak base and its conjugate acid, so this is a buffered solution. So we have pH equals pKa plus log base over acid. So this is our base, this is our acid. Okay, but we do need to go through and find the pKa. So we were given the pKb, and like we just talked about, pKa plus pKb equals 14. So if we do 14 minus pKb, that will give us our pKa. Okay, and if you'll notice, this is very basic, which should make sense because I just told you this is a basic buffer. So we can go ahead and plug this in. pH is equal to our pKa plus our log of our base over our acid. So again, this is just the same thing. Instead of having acid and conjugate base, now we have base and conjugate acid. But it doesn't matter because we're still looking at which one has the acidic properties, which one has the basic properties. So if we go ahead and plug this in, we can get the pH of our buffer. And again, this makes sense because we have slightly more base than we have of our conjugate acid. So it should be slightly more basic than our pKa, because again, if they were equal, pH would equal pKa. All right, just a couple more topics for this. If we're looking at making a really effective buffer, okay, a great buffer would neutralize moderate amounts of acid or base. Not like super large amounts, but small amounts of an acid or a base. But like I said, there's a limit to how much can be added before we can overwhelm our buffer. So the buffer capacity is the amount of acid or base that our buffer can neutralize before, like I said, we overwhelm it. So buffer capacity, you want a really high buffer capacity so that you can, essentially absorb the effects of either added acid or base. And then the buffer range is going to be the pH range in which buffers can be effective. Like I was alluding to earlier, sometimes you might want an acidic buffer for your reaction. Sometimes you might want a basic buffer for your reaction. So you want to pick a good acid, a good acid conjugate base pair to go with your reaction. And that's all going to depend on Ka. Because again, if we look at our Ka, right, we can find our pKa. And I told you if you have equal amounts of your acid and your base, then your pH will be equal to your pKa. So say your reaction needs to, be at pH 5. That's when your reaction works wonderfully, pH 5. Well, okay, you would go find an acid that has a pKa around 5. And then you would build your buffer out of that acid and its conjugate base, and that would be, what you would do your reaction in, as long as it's not going to interfere with your reaction. And our effectiveness of our buffer depends on two different factors. One, the relative amounts of buffer acid and base. So that means the amounts compared to each other. This is what I was telling you, that you want them to be the same a lot of times. There are instances where you would want them to be different, but a lot of times we want them to be the same so that they can, absorb the effects of an acid or a base. And then the absolute concentrations of the buffer and the base. We want these to be high. This is telling you essentially that you want to have large amounts, like a high molarity of your acid and your base in order to be able to neutralize any acid or base that's being added. Because again, we're going to do those reactions in moles. So the higher the molarity of your acid and your base, the more moles per given volume that you have in there. So buffer capacity, a little more about that. Like I said, it's the amount of acid or base that can be added to a buffer without causing a really large change in pH. And that large change in pH would be overwhelming our buffer. That would be adding more moles of strong acid or more moles of strong base than we have of our weak acid and our weak base. Our buffer capacity increases with absolute concentration of the buffer component. So we want a really concentrated buffer because, again, that means there's going to be a large number of moles of our weak acid and our conjugate base in there that can react with our strong acid or strong base that's being added. If you have a really dilute buffer, then even just a couple drops of acid or a couple drops of base might be enough to overwhelm your buffer. So you want to have a really concentrated buffer, high molarity. Like I was talking about, our buffer is usually going to be most effective when our ratio of our acid to our base is 1 to 1, because then it can, neutralize added strong acid or it can neutralize added strong base. Our buffer is considered to be effective when our ratio is between 0.1 and 10. Okay, and again, our buffer is going to be most effective when our concentrations of these acids and bases are large. So like I said, we want to have the ratio between 0.1 and 10, and if we plug those values in as our ratio here in the Henderson-Hasselbach, we will get that we want our pH can be pKa minus 1 or pKa plus 1. And so an effective buffer will work plus or minus 1 pH point from our pKa. So again, like I was telling you, say our imaginary buffer we made was pH 5. That means that our buffer would be really effective between 4 and 6. But outside of that range, it won't be very effective. So again, when you're choosing an acid to make your buffer, you're going to figure out which one has a pKa that's really close to the pH of that buffer that you need. So again, we want our ratio to be 1 or as close to 1 as possible so that we can neutralize either added or base, right? Sometimes though, we may want one that's just going to neutralize any added acid. Well, okay, then we might make it a little more heavy in our conjugate base because we know we are going to add a bunch of acid to it. The opposite is also true. If we know we're going to add a bunch of base, we might make our buffer a little bit heavier in our acid, right, in our weak acid, so that it can neutralize more of that strong base. But most of the times, we're going to want them to have equal amounts of both acid and base so that they can, prepare for whatever comes their way. And that is it for today's slideshow on buffers. So we've covered a lot of ground today. We've talked about what a buffer is. We've talked about how to do a lot of calculations associated with buffers. Mostly we've talked about how to use the Henderson-Hasselbach in these equations. And I told you whenever you have a buffer problem, when you've got strong base or strong acid being added to your buffer, the first thing you're always going to need to do is write out that neutralization reaction, do an ice table in moles, and then use that Henderson-Hasselbach equation to calculate the pH. Make sure you're getting really good at doing these buffer calculations. The next part of this chapter is titrations, and we're going to put together a lot of different pieces that we've worked on throughout the semester and even a little bit from Chem 1 to do these problems. We've got, weak acid equilibriums, weak base equilibriums, we've got pHs with strong acids and bases, we've got neutralization reactions, we've got buffer problems, we've got all of this coming at you in this next section. So make sure you're getting really solid at buffer problems so that you are prepared that when we get to titrations, you're a pro at buffers, just like you are at all of the equilibrium problems we've been working on thus far. You have a lot of lecture worksheet problems to work on buffers, so make sure you're working through those. And as always, if you're getting stuck, please send any questions my way. I am happy to help you keep working through these problems. So get lots of practice, and I will talk to you all next time.